Pre-Calculus Virtual Day 24, April 22nd, Chapter 4.3 and 4.4, working on logs. So you were introduced to this in Math 3. Logs is the inverse of an exponential function. This is logarithmic form, and this is exponential form. You're going to be required to go back and forth between logarithmic and exponential form. So we're just going to start with converting to logarithmic form. There's a trick that I found on Pinterest a couple years ago where you kind of sort of make an L. You start log base 1.2 of m is, what is your exclamation point? It's more of a G sort of thing. Log base 1.2 of m equals 3. When it says to convert, no solving involved. That's all you gotta do. Here, log base e of 9 is b. Log base e is then natural log. Don't leave it as log base e. I need to know that you know that's the natural log, so we're saying the natural log of 9 is b. That's an L, not a 1. Converting again, log base a of 24 is 4. We'll use this conversion when we're solving equations for the most part. Converting to exponential form, you're going to make an e, start with your base, and then circle around. So a to the 5th power equals 4. E to the negative 3rd power equals b. Now, normally this would be written as the natural log of b is negative 3. You would need to know that that is base e. Okay, and then here, 3 to the c power equals 4. We also need to know that the common log, if it doesn't have, you have something like this, that is called the common log, and it's an understood base of 10. That's what the log button in your calculator does. So, finding the exact value, on my other calculator, you're going to convert and set it up as an exponential equation where your variable's on the outside. So we're going to make this exponential. 2 to the y equals 16. And then solve like we did before where we changed our bases. 16 is equal to 2 to the 4th, so we have 2 to the y equals 2 to the 4th power. We have the same base, so we can cancel those out. Y equals 4. Here, 3 to the y equals 127. 27 is the same thing as 3 to the 3rd power. So you have 3 to the y equals 1 over 3 cubed. Because it's in the denominator, you can move it to the numerator and put a negative with it. We have 3 to the y equals 3 to the negative 3rd. Cancel those out. Y equals negative 3. So because the log is the inverse of the exponent, and like we started this unit with the exponents, or with inverses, the domain of logs is the range of the exponents. Range of logs, domain of the exponents. The domain of the exponents, remember, was always all real numbers. So the range of the logs is going to be all real numbers. Okay. This is the parent function. Domain is going to be from 0 to infinity, whereas exponents had a horizontal asymptote. All right, so this is here. Exponents has a horizontal asymptote. Logs are going to have vertical asymptotes. Just the opposite of what you started with, where you switch x and y, so that's how that works. Finding the domain. So since we have a vertical asymptote, and this shifts us to the left 3 places, a vertical asymptote would normally happen at y equals 0. So because this is shifted left 3, we are going to have a vertical asymptote at x equals negative 3. Remember, flip the sign of h. We had log base b of x minus h plus k. So our domain here is going to be from -3 to infinity. You can type this in your calculator to verify. I'm going to use the other calculator because my one doesn't have log exponent. And we're solving equations, you'll need that. Oh, it's going to. So here we go. We have log. So to get to log base, you're going to go to math. And then down to the bottom, you see that log base 2 of x plus 3. And then graph it. Now your calculator is not as accurate as your eyes, and as it can only zoom in so far. This does not stop. It does keep going down. It's just going to approach that asymptote. You can see that better on Desmos. Here, just like a rational equation, we have a 0. So at the numerator, so 1 plus x equals 0, this would be where your fraction is 0. And we would have an asymptote here at 1 minus x equals 0. So here you would get x equals -1, and here you get x equals 1. So those are going to be our stopping points. We plug that in. You cannot take the log of 0. So where you plug something into an exponent, you can never get 0 out. So the reverse of that, the inverse of that, is you can't take the log of a 0. So we have math log base 5 of 1 plus x divided by 1 minus x. You can see what this is going to be. It's kind of hard to see with the light, sorry. Maybe that's easier. No. It's a little, ooh, there we go, sort of. It's sort of like a cubed function, but it stops. This domain is only from -1 to 1. It looks like this and stops. Okay, here we have the absolute value, so this means it has to be, we want that to be greater than 0 because this cannot be equal to 0. So we get x is less than, -x is less than 0, and x is greater than 0. So that means that x is going to be less than or greater than 0, but not equal to 0. So we get x such that x is not equal to 0. Domain, positive numbers, range, all real numbers. X-intercept is 1. There's no y-intercept unless there's a shift. We have a vertical asymptote. It is decreasing if a is between 0 and 1, if your base is between 0 and 1, and increasing if a is greater than 1. Always contains these points if a is, or if there are no shifts or reflections, and the graph is smooth and continuous. This says that the natural log, y equals the natural log of x. Sorry that got cut off. Y equals the natural log of x if and only if x equals e to the y power. So, and remember the natural log, like we said, is equal to the log base e. Be careful with your bases here. There's bases, the 2, the 5, the 1/2, the e. Those are subscripts, which means they're smaller and to the bottom. It's like the opposite of an exponent. Moving on, I'm going to start by graphing. This one is a reflection with respect to the x-axis. And this +2 means we're going left 2. So our parent function, y equals the natural log of x, we would have a vertical asymptote at 0. So this means we're going to have a vertical asymptote at x equals -2. Sorry, that didn't quite go through there. Our domain here is going to be from -2 to infinity. because we're reflecting that with the x-axis, not the y-axis. My range for these is always all real numbers, from negative infinity to infinity. And then I'm just going to put points on my calculator here. I'm going to use my other calculator because I think you can see it a little better. Since I showed you my bases, that's the main point of the one I was showing you. So negative y equals negative natural log of x plus 2. So instead of increasing, this one is going to be decreasing. And it approaches here negative 2 on this side. So my table, I have the point negative 1, 0, 0, negative almost 0.7. And it's going to go like this. This does keep going, despite what the graph says. Your graph is not as accurate. Only so many pixels it can show you there. So it's hard for it to show you that it is getting closer and closer because it gets there so quickly. This is the common log. We talked about that already. Log base 10. So what we've got here is log base 10. We have 3 log of x minus 1. This is a vertical stretch. It means it's growing more quickly. And this means we're going right 1. So we have a vertical asymptote at x equals 1, which means our domain is going to be from 1 to infinity. Our range is still all real numbers. And because there's no reflection there, we are going to be increasing. So 3 natural log, you can choose the log button on your computer. Sorry. 3 natural log, or common log, of x minus 1. And it's going to look like this. So I'm going to look at my table for some points. We have the point 2, 0. Again, we have our vertical asymptote at x equals 1. We have the point 2, 0. And I'm just going to do 0.5. Or I'm sorry, I'm just going to do the next one. 3 is almost a 1. 0.9 roughly. And it's going to go like this. Now we're going to solve some equations. A, whenever your variable is inside here, it's going to be easiest to convert it to exponential form and solve. So converting that, we have 3 squared equals 4x minus 7. 9 equals 4x minus 7. Add 7, 16 equals 4x. Divide by 4 and you get x equals 4. Over here, I'm again converting to exponential form. X squared equals 64. Take the square root, you get x equals plus and minus 8. The only time that you need to be careful about your plus and minus or your negatives is you cannot have, so what you're taking the log of has to be greater than 0. So this here would have to be greater than 0. This whole expression, not just x. 4x minus 7 has to be greater than 0. So if you get something out, so if your x here had been where the 64 is, it could have only been positive 8. It could not have been negative 8 because you can't take the log of a negative number or 0. Okay. A little bit more here. Solving another one, you have e to the 2x equals 5. Your best bet here, you can convert it to exponential or to logarithmic form, or you can just take the natural log of both sides. So what I'm going to do is take the natural log of both sides. So if I take the natural log of e to the 2x equals the natural log of 5, you can use the power rule, which says if you take this guy and bring him out front, with logs, if you have an exponent in a log, you can bring it out as a coefficient. We have 2x times the natural log of e equals the natural log of 5. The natural log of e cancels out as they are inverses of each other. It's like multiplying and dividing by 5 or something at the same time. You can check that in your calculator. You get 2x equals natural log of 5. Divide both sides by 2. And then plug this in your calculator. You want to make sure that you end your natural log parentheses before you divide by 2. So natural log of 5 divided by 2, 0.805. You can check this by plugging it back in. If you have e to the 2 times 0.85, that should give you close to 5 because we rounded. So there we go. An application problem. So this is very similar to the one we did yesterday with exponentials, but this time we're going to have our y value, so we're going to solve using logs. Excuse me. All right. The concentration of alcohol in a person's blood is measurable. Recent medical research suggests that the risk of having an accident while driving a car can be more than R is your risk. Okay? And X is the variable concentration of alcohol in the blood. K is a constant. So suppose that the concentration of alcohol in the blood of 0.04 results in a 10% risk. So we're going to find our K, our constant. So a 10% risk is R equals 10. So it's giving you that means that it's not 0.1, it is 10. So we have 10 equals 6e to the K, and then our X value is our concentration of alcohol, 0.04. So now I'm going to solve this for K. So I'm going to divide both sides by 6 first. And I'm going to simplify this fraction. So you have 5 thirds equals e to the 0.04 K. Take the natural log of both sides like we did in the question above. So we have the natural log of 5 thirds equals the natural log of e to the 0.04 K power. Bring these out front as a coefficient using the power rule, and natural log of e cancels out. So the natural log of 5 thirds equals 0.04 K. Divide both sides by 0.04. And you get K equals, I'm going to round that here. So natural log of 5 thirds in your calculator. And then divide by 0.04, 12.771. What is the risk if the concentration is 0.17? Remember the concentration, that is your X value. So I'm putting that in for X. So what is my risk? So I'm going to use this as my K. Oh, I'm sorry, this is my K and this is my X value. So this gives us the equation R equals 6 times e to the 12.771 X. So now my X value is the 0.17. So 6e to the 12.771 times 0.17. And you can just plug that in your calculator, exactly like this. E to the 12.771 times 0.17. And you get 52.6%. So if your concentration, if your blood alcohol content is 17%, you have a 52.6% chance of getting into a wreck, is what this is saying. What concentration of alcohol corresponds to a risk of 100%? So this is our R, we are looking for X. So 100 is going to equal 6 e to the 12.771 X. Divide both sides by 6. Simplify that and you get 50 over 3 equals e to the 12.771 X. Now you're going to take the natural log of both sides. So the natural log of 50 thirds equals the natural log of e to the 12.771 X. Using the power rule to bring that out and then canceling those, the natural log of 50 thirds equals 12.771x. Divide by 12.771. Plugging this into your calculator, you have to put the 50 thirds in parentheses. It'll already do that for you, but you have to end those before you can divide by your 12.771. So you can't see that. And you get 0.22. So a blood alcohol content of 22%. If the law asserts that anyone with a risk of having an accident of 20% or more should not have driving privileges, at what concentration of alcohol in the blood should a driver be arrested and charged with a DUI? So this is going to be our risk, and we want to know what the concentration should be, so that's going to be our X. So 20 equals 6 e to the 12.771 x. And we're just doing the same thing we just did. Divide both sides by 6. Take the natural log of both sides. Bring this out front, cancel those out. Divide. And then type it in your calculator. 0.094. That is all for 4.3. We have one more little section we're going to look at, and that's just property of logs, and that is 4.4. Property of logs. So to show that this is always the case, no matter what the base is, we can put this in exponential form. A to the 0 equals 1, and that follows our exponential property that anything to the 0 power is 1. Here, we'll look at it the same way. A to the 1 equals A, and that is anything to the first power is itself. So it doesn't matter what the base, what A is, as long as they're the base and what you're taking the log of are both A, then the answer is 1. And here are our properties. So we just looked at the first two. The next one, if you have something, so an A to the log of the same base, then those two will cancel out and you'll get just whatever you're taking the log of. Here, if you have the base and the A are the same, then whatever your power is here is what your answer is. That also works because if you bring that out front, then you know that this has to be 1, right? So you can think about that way. This is the product rule. So if you take the log of a product, it's equal to the sum of the logs. You split it up, they both get a log. Multiplication translates to addition. Division here translates to subtraction. The quotient of the log is the difference of the logs. And then the power property, which we've been using. So expanding means we're just taking this and making it longer using more than one log. So I'm going to say this and these are multiplied together. So I'm going to use the product rule. So I have a log base A of x plus log base A of, and I'm going to rewrite this radical here as a power. So you have x squared plus 1. Remember, it's always power over root. So since it's a square root, it's 1/2. Then I can take the power rule and pull that 1/2 out front of that log. So I have log base A of x equals 1/2 log base A of x squared plus 1. I can't go any further because this is addition. That stays the way it is. Oop, not equals. That could be a plus. Sorry about that. Here, I have the natural log, I have a quotient, so I'm going to subtract the natural logs. Then the natural log of x squared minus the natural log of x minus 1 to the third. Use your power rules, and you get 2 natural log of x minus 3 natural log of x minus 1. And then the last one that we're going to do that for, same situation, just a little bit more. So I have a log base a of x cubed plus, if it's on the numerator, it's positive. If it's on the denominator, it's negative. You think about with your exponents, your exponential rules, if it has a negative in the exponent, you move it to the denominator and get rid of the negative. So the denominator has a negative exponent, which is essentially what logs are. Plus, and then I have the log base a of x squared plus 1 to the 1/2 power minus the log base a of x plus 1 to the 4th. Then I'm just using the power rule. So I have 3 log base a of x plus 1/2 log base a of x squared plus 1 minus 4 log base a of x plus 9. Compressed logarithms or condensed logarithms is essentially the opposite of what we just did. You're making them into one log. So you have to start with, the last thing we did was power, so you have to start with that. So this 4 is going to come up as an exponent first. Log base a of 7 equals plus log base a of x plus 1 to the 4th. Addition translates to multiplication. So I have log base a of 7 times x plus 1 to the 4th. Typically, when you have a lot of stuff, you'll put brackets around it so that you know you're taking the log of the whole thing. B, same situation. Bring up my power first. The natural log of 8 to the 2/3 minus the natural log 3 to the 4th minus 8. Subtraction translates to division, so I have the natural log of 8 to the 2/3 over 3/4 minus 8. These are all numbers, so you can plug that in. 8 is 4, and then 3 to the 4th minus 8 is 73. So you get 4 on top, 73 on the bottom. The only reason you can do that is because there are no variables. That last one, log base a of x plus log base a of 9 plus log base a of x squared plus 1 minus log base a of 5. So this here gives us multiplication. So we have log base a of x times 9 times x squared plus 1. The minus gives us division, so that's going on the denominator. And then I'm just going to write that a little bit neater. So I have log base a of 9x times x squared plus 1 over 5. And that's going to be our answer. To approximate, we're going to do this by hand. So I'm going to convert this to exponential form. 2 to the y equals 7. Well, I know that 2 cubed is 8. So y is going to be about 3, a little bit less than 3. You can use the change of base formula, which is right here, or log base on your calculator to determine what y actually is. Log base 7 over, no, not log base 7, log of 7 over log of 2. Plug that in your calculator. And you get 2.807. Change of base formula is not necessary with the calculators that we have now, but you will see it, and it's handy when you're solving equations to know the change of base formula. So if you have, on my calculator, for example, if I go to math, I do not have that log base option that was on the other calculator. The only log button I have is the common log, which is base 10. So if you have a log with a different base besides 10, you can rewrite it as the common log of what you're taking the log of divided by the common log of your base. Okay, and that also works for the natural log. And this is a photo. Sorry about that. So approximate. So I have the log of 89 divided by the log of 5. And then just plug that in your calculator. 2.7889. It will tell you how many decimal places typically. If it doesn't, just use 3. Here I've got the log divided by the log square root of 2, which is 2.3219. And then the last one is on the calculator. I'm going to plug this into my y equals using the change of base. You don't have to do that if your calculator has log base, or you can use Desmos. So I'm just plugging it in my calculator. Have the log of x divided by log 2, and it will show it to you. It's just log base 2. There are no shifts left and right. It's just a normal log. The inverse of this, just a side note, is going to be y equals 2 to the x. That would be the inverse equation. So if you don't have questions, if you do, please holler, let me know. Happy to help you. Make sure you get that homework done, and take care.